In today's class, I want to talk about the connection between optimization and the gradient and the Hessian. So, what information can the gradient and the Hessian give us about local and global minima of functions? Right? So, the framework that we want to operate in is the following. So, we are given a function f, say from Rn to R, but this can be generalized. Let's assume that f is well defined over the entire Rn, and in some cases I'll assume that the gradient of f is defined over all of Rn, and perhaps the Hessian may or may not be defined over all of Rn. And let's consider a situation where we want to find minimum of f of x subject to some constraints. Right, so the typical problem that we encounter is we want to minimize f of x such that x satisfies some particular constraints. And as we've seen, one way of modeling constraints is using the functional form. Right, so we could say that overall x such that maybe f1 of x is less than or equal to alpha 1, f2 of x is less than or equal to alpha 2, some fm of x is less than or equal to alpha m, and so on. That's one way of representing a constrained optimization problem or a constrained minimization problem, right? But equivalently, these constraints define some set. Okay, that's what we call the constraint set. So the same as saying we want to find minimum of f of x such that x belongs to some set. Let's call it omega. Okay, omega is our constraint set. So today will be a little less ambitious, and suppose someone gives you a candidate x star, and you want to determine whether that particular x star could be a minimum or not. Okay, there's one problem which is searching for the minimum. The second problem is someone presents you a particular value x. You want to know whether this x is a minimum or not. So, first problem is find the minimum or the solution. The second thing is given some particular x that satisfies the constraints, is x a solution? Okay, so the first step, I'll relax conditions on f. I won't say that function is convex or anything of that sort. All right, in this situation, can I say something about whether a given x is a candidate solution or not? Now, in general, it is hard. If all you know is x and maybe some local information about the function values around x, it is not possible to say whether f is actually a minimizer or not. But what we can say is whether f is a local minimum or not. Right. So first I'll have to define what it means to be a local minimum. Correct? So is the problem clear? All right. So first, even before I get to the concept of a local minimum, I'll introduce something else, which is, suppose I'm at a given point and I want to know whether this is a local minimum or not, whether it's a candidate solution or not. I also need to know, if I were to look for a candidate solution, where should I look? Can I look all around myself or all around this point, or are only certain directions valid directions? Right? Because if I'm sort of in the interior of omega, then every direction is a valid direction to look for a solution from that particular point. But on the other hand, if I'm on the boundary, I can't go outside the constraint set. That I'm not allowed to do. I can only look within the constraint set. Right? So the geometric picture is the following. So I'm given some sort of a constraint set. This is my omega. And I give you some point on this particular constraint set. Maybe this particular point. This is my point x. Now what I can do is, given this particular x, I can try to look in all particular directions and see if in those directions, if I sort of move a little bit in that particular direction, is the function value increasing or decreasing? Okay. So suppose I'm sitting in the interior of omega, and it so happens that no matter which direction I look, the function value is only increasing. Then I could sort of safely assume that this is a candidate solution, that's a local minimum. Okay, because no matter which direction I look, in all directions, the function value is only increasing. But I can't say the same when I'm at the boundary, right? Because I should only be looking within omega. I'm not allowed to look outside omega, because after all, I'm trying to solve a constraint optimization problem, a constraint minimization problem. So if I look inside omega, that is, if I look at any of these directions, if the function value is increasing, then I can conclude that this is a local minimum, right? So I'm allowed to go along the boundary, or I'm allowed to go inside omega. But if the function value is, say, decreasing in this particular direction, then I don't want to consider that, because I can't treat that as a solution, correct? So the point that you need to keep in mind is that given any constraint optimization problem, the optimum value could be within the interior of omega, or it could also be a boundary point. And it is really the boundary points which are tricky. That is what you need to be most careful about. All right. So directions outside, that take you outside omega, are not valid directions to consider. So I'll define this notion of a feasible direction. So we say that some vector v in Rn. Now I may want to say that the norm of v is equal to 1, just because it's a direction vector, but that's not, at least for the purpose of this definition, that's not required. Okay. So, but it doesn't hurt to impose this constraint that the norm of v is equal to 1. So we say that v is a feasible direction for f at some point x. Again, implicitly, we're assuming that we're operating with some constraint set omega. If basically I can move along v up to a certain point. It could be that, for example, I could stay here. If I start from this, if this is my point x, then I can move up to a certain limit in this direction, right? Up to this point, I can go from here to here in this direction. But beyond that, I can't. So I'm not allowed to go arbitrarily far in a particular direction, but I should be able to travel some distance along that direction and still remain within omega. Okay. So for instance, this is a feasible direction for f at the point x, but this is not a feasible direction for f at x. If if basically I can find some alpha which is greater than 0 such that x plus delta times v belongs to omega for all delta between 0 and alpha. We make a slight change since this has nothing really to do with f. Let's say that the feasible direction for omega at x. Okay. So remember that x plus delta v for delta greater than or equal to 0 is, as you increase delta, so the set of all x plus delta v delta greater than or equal to 0 is a ray, correct, which originates at the point x and goes along the direction of v, correct. So this would be the direction of v and this is the point x. So essentially this is telling me that there is some line segment with one point being x and this line segment is in the direction of v, and this is a non-trivial line segment. Is this much clear? Okay. So that's a feasible direction. And which one? So one point is that we're typically going to look at typically going to start from points x which are already within omega. So essentially x will belong to omega.
Direction doesn't make sense.
So remember that this is implicit, right? So v is some non-zero vector. Whether I include 0 or not doesn't really matter. What I want is that alpha is strictly greater than 0. That is all. So using this, so we say that x star is a local minimum for f comma omega. Of course, we have a function and we also have a constraint set. If exactly what I said earlier happens, you start from x, you move in any valid direction, that is, you move along any feasible direction. If there is some neighborhood within all feasible directions where the function value can only increase, it doesn't decrease any further. Okay, sure.
Putting 0 mean that all directions are true.
Which one?
For all
Sorry, wait. Yeah.
I made a mistake.
Okay, yeah. So one thing is that each of these alphas can potentially depend on v. right? If that is what is. So this delta, so this whole statement is for one particular direction v. For a different v, the corresponding alpha v could be different, right? For example, in this direction, I can move much further while staying within omega. But the only guarantee that I require is that I'm able to travel some distance, some non-trivial distance in that direction while still satisfying all of the constraints. All right. So we say that x star is a local minimum for this constrained optimization problem if basically the same thing happens. If there exists some, if for every feasible direction v, we can find some beta v greater than 0. This beta v could be different from alpha v, okay, such that f of x star is less than or equal to f of x star plus delta times v for all delta between 0 and beta v.
Why are you putting beta dependent on the V? You could have done like a homogeneous ball kind of.
I could, but again, this is in some sense more general. Yes, question? It's with respect to the function as well as the constraints. The domain, I'm assuming that the domain of f is at least a superset of omega. Correct. So x star is a local minimum. I'm assuming that x star is a point in the domain, right? In fact, it's a point within the constraint set which lies within the domain and also lies within the domain, right? And f of x star is whatever the minimum value. Okay. I'll say that x star, again, I'll go back and forth between f of x star and x star. I'll use those terms a bit loosely. Okay. I'm sorry?
We can say as local minima is.
Sure. I'll use both terms. I'll use the term local minimum interchangeably for x star as well as f of x star. Okay.
You have a circle, as you said.
Yeah.
And take a point on a circumference.
Okay.
Is the tangent direction a feasible direction?
Okay. The tangent direction is, I get the problem. So typically we're going to assume that this set has some sort of a non-empty interior, just to avoid the sort of example that you are giving, right? In a sense, for the particular example that you gave, right, no direction on the circumference is a feasible direction.
Or inside?
How? No, assuming that, okay, I'm assuming it's only the circumference.
Okay.
Yeah, the no direction is a feasible direction.
We could have a local.
Where
If some function is defined on the circumference.
if some function is defined on the circumference, potentially yes. Right. That's why I will typically want a set with a non-empty interior. So for that specific example that you have, so if you take the entire circular region, that the region enclosed by the circle, then a region along the direction along the tangent would not be a feasible direction. But anything that points inwards is a feasible direction. Which one? VR. So in this case, yes. You have
boundary points also will be checked.
we will, as you'll see, we will. Okay, so again, we'll run into problems if the function is not smooth in some sense, right? So I will require all of these sort of regularity conditions. That is, the function typically we'll work with functions that are convex, or we'll at least work with sets that are convex and functions that are reasonably smooth. At least maybe the first derivative exists. Okay. But I agree, all of these points are something to be kept in mind. You can this particular definition for a local minimum may or may not be okay in certain cases. So another way of defining a local minimum would potentially be the following. I could say that f x star is a local minimum if f of I could say that x star is local minimum if f of x star is less than or equal to f of x for all x that lie within, okay, I should say if there exists epsilon greater than 0, such that f of x star is less than or equal to f of x for all x that lie within a ball of radius epsilon but within the constraint set. Okay. So this is something that would handle any irregularity conditions on f, on omega. That wouldn't matter. Okay. But for our purposes, when the function is sufficiently regular and the set is typically convex, this definition is okay. In certain cases, you can show equivalence between these two definitions. I want to use the first definition because it is kind of more natural when we talk about conditions in terms of the gradient. Right? Because we're going to assume that the function is sufficiently smooth and you're going to have enough directions to look for. This definition is nicer to work with. And in some ways, okay, there are multiple reasons. One is, of course, when functions are sufficiently nice, this is easier to work with. Another reason is that geometrically, this is kind of intuitive in some ways. But the third reason is this is typically going to be how many of the algorithms, optimization algorithms work. You start at a particular point, you pick a direction, a valid direction, and move along that direction to see if the function value decreases. Okay. Typically, you pick a feasible direction where you're sure that the function value decreases and move a certain distance along that direction. and you do this iteratively. So that is why defining things in terms of directions and so-called step sizes makes sense, because this is a in the context of optimization, this is a useful definition to work with. But more generally, this alternative definition may be something that's more solid, because it works irrespective of whether f and omega are nice or not. Any other questions? All right. So before we see conditions on for a point to be a local minimum or not, in terms of the gradient, let's quickly recall some concepts that we require. So suppose that f is some function from Rn to R, and the gradient exists at x. At x, v is, let us say, some direction. So it's just some unit norm vector. Then what is the directional derivative of f at x along the direction v? So it's basically just the inner product of the gradient with the direction v. Or gradient of f transpose times v. Okay, so that's something that we'll require. The second thing that we require is the following. So suppose, and this is something that we'll use very frequently. So suppose I have f is a function from Rn to R. We'll frequently want to look at the function, let me call it phi v. So the function f along the direction v, phi v of, let's say, I want another term, let me call it tau, or let us use t. This is going to be equal to f of x plus v times t. Okay, so essentially I'm picking a point, I'm picking a direction, and I look at this one dimensional function phi of t, which is the function f along this particular direction. So it's like taking the function and taking a slice of that particular function. Okay, so here's an exercise. If f is a convex function, then for every direction v, phi v of t. So for every v and every x, phi of x plus vt, and this is defined for t in R. This is a convex function. Okay. So for every v, so for every point, and you look at any direction, for every direction v, you essentially you take a convex function and you take any slice of a convex function, then the corresponding slice also is a convex function over R, right? So that's also a useful property, and in fact the reverse is also true. That is, if phi v of t is a convex function for every v and every x, then f is also a convex function over Rn. Right? Okay, so using these notions, let's see what are the conditions for which a particular point can, under which a particular point can be a local minimum. So we'll first look at, I'm sorry,
Can you draw a diagram?
for, okay, let's just take, for instance, f of x to be equal to, say, x1 square plus x2 square. Okay, so this is some particular point. So this is just the quadratic function, right? Now, what is phi v of t going to look like? This is x plus vt. Let's pick a particular v. In fact, even here, it is not necessary for v to be a unit norm vector. It's okay even if v is not a unit norm vector. So this is x1 plus v1 t the whole square plus x2 plus v2t the whole square, right? For some fixed x1, v1, x2, v2, which is, again, if you, let's try to expand this out, you get x1 square plus v1 square t square plus x2 square plus v2 square t square plus 2 x1 v1 t plus 2 x2 v2t. So this is a quadratic in t. So this is v1 square plus v2 square t square plus 2 times x1 v1 plus x2 v2 times t plus x1 square plus x2 square. Okay. So another way of thinking about this is, if you sort of look at the contour, right? Let's say x1 minus 2 to 2, x2 and f is equal to x1 square plus x2 square. Right? Perhaps I should right. This is sort of a visualization from the top, right? So darker values means that the function value is smaller, and lighter values means that the function value is larger. Better. Right, so it keeps increasing. And what does this particular phi v of t look like? Let's say that I take a slice of this along, say, just take a cut. Okay, the cut would mean that if I go along that line, the function is just something like a parabola, right? Into if I look at this as a function of x1 and x2, this is basically a three-dimensional parabola, right? It's like a bowl. Okay, now let's say I take a slice of this. If I take a slice of this, I essentially get just a single curve, a one-dimensional curve. Right? That is my phi v of t. Right? If I take any slice, if I take any cut along any direction, that gives me one slice, it gives me a one-dimensional function. And that each of those functions is a particular phi v of t. Is that clear? Any other questions? Okay. All right. Since we are almost out of time, we'll have a quick quiz.